Hi, I'm Matthew Roberts. We're presenting with Zach Bussard, Andrew Goen, Jonathan Bowman, and today we're going to be presenting on the concept of the instantaneous center of zero velocity. The instantaneous center of zero velocity is the point on a rigid body in general plane motion that has zero velocity at that instant. It's also the point that the body rotates about.
Hey guys, I'm Andy. Now you might be wondering why the instantaneous is important. Well, if we have the instantaneous center and a velocity on a body with a perpendicular distance to the IC, we can calculate using this equation, the omega. And since omega is a body property, we can use that to find velocity anywhere on this body.
In order to find the instantaneous center of zero velocity, all you have to do is draw a perpendicular line from the velocity vectors. We have three general cases. When you draw a perpendicular line from the velocity vectors, you're going to make a triangle. So you're going to want to brush up on your basic trigonometry. Some useful equations that we wrote out are the Pythagorean theorem, which is only for right triangles, the law of sines, and the law of cosines. For case 1, it's fairly simple. We have two parallel vectors, and they're in the same direction. So as you can see, we drew a line perpendicular to the two vectors, and we drew a line connecting the two tips. This point of intersection is the instantaneous center. Case 2 is very similar. We have two parallel lines again, but they're in opposite directions. So this time, connecting tip to tip and drawing a perpendicular line, the instantaneous center is located right here.
Hi, I'm Zach, and I'm going to show you the third case. The third case is when we don't have two velocity vectors that are in the parallel directions. In this case, you'll just do the same thing where you drew a perpendicular line from each velocity vector, and where they meet in the center is the instantaneous center of zero velocity. Here you can see in our physical representation that this is a lot like the third case, where we have got two sliders. Each one can only have velocity in a direction perpendicular to the other one. So here you'll see that we draw a perpendicular line from each slider perpendicular to its velocity, and where they meet is the instantaneous center. And so here you can see, as we move these two sliders, you can see that the instantaneous center is not at one point for the entire motion. Okay, so we use SolidWorks to model this contraption together, because in order to have an instantaneous center, you have to have velocity. So what we did is we used SolidWorks to give a velocity to this slider here, a constant velocity, and then using the motion analysis software as part of SolidWorks, we were able to graph this velocity.
Hello, I'm Jonathan. I'm going to talk to you about using this as a practical solution for problems. So here we're given a length of an arm of 78 millimeters, a known height of 20 millimeters, and a known velocity of 10 millimeters per second. We know this is a right triangle, so we're able to plug it into our trigonometric equation of Pythagorean theorem. This gives us a length of this arm of 75.4 millimeters. We then plug that into our equation up here, where we have a velocity of 10 millimeters per second and a length of 75.4 millimeters. This gives us an angular velocity of 1.133 radians per second. We then plug this into our equation down here, where we have the angular velocity and our arm length of 20 millimeters. This gives us a velocity of the other slider of 2.66 millimeters per second. You can use the IC to find velocities of different components and the angular velocity of your arm.